Thank you. So I am indeed Russ Olsen, and I want to talk to you about functional programming this morning. Just briefly about me, I am kind of a programming language geek. I have been learning programming languages and occasionally writing books about them for most of my career. And lately, I've been doing functional programming. So a couple of things about this talk before I really get started. You might be thinking, functional programming in 40 minutes. How is he going to cover functional programming in 40 minutes? And I'm thinking, what am I going to do with the last 10 minutes? Because I think the whole theme of this talk is that functional programming has been mystified, and people get very excited about new technologies or technologies that are new to themselves, and they start talking about them in big, expansive terms about how it's going to change everything. And in fact, functional programming really is a fundamentally simple idea, and that's what I'm going to try and get across this morning. I do want to warn you that I'm a Clojure programmer, so my flavor of functional programming is with Clojure. So necessarily, my point of view and what I'm going to tell you is going to have sort of a Clojure spin to it. I am going to try to point out in places where this is the way Clojure does it and other programming languages do it differently, but keep in mind that I'm kind of a Clojure programmer. So I really want to cover three things this morning and really one main thing. And the main thing is, what is functional programming? Where did it come from? Like, what's the ideas behind functional programming? How did we come to them? And that's most of what I'm going to talk about this morning. And then from there, I'm going to move on to what's it like to be a functional programmer? What's it like to actually do it? And in particular, what's it like to do it as a beginner? I'm maybe from the object-oriented tradition, and I start programming in a functional style. What's that like, that transition like? And then finally, I'm going to try and answer the question, which is maybe a little subjective, which is, does it work? Can you make it work? And again, I'm sort of a practical software engineer. I write applications for my day job. And so this is going to be a sort of functional programming for ordinary programmers who want to write applications and libraries. So let's start with what it is. And so when I was first getting involved in functional programming, you Google functional programming, how do I learn functional programming? And there was one thing that I saw over and over and over, and it is functional programming. Forget everything you know about programming. Or, even worse, functional programming. Forget everything you think you know about programming. Yeah, well, we're all, I think, software developers, programmers here. It turns out we know quite a lot about programming. What do we know about programming? We know about things like programs are full of names, and you assign values to those names. Programs are full of conditional logic, they're full of iteration, they're full of procedures and subroutines and things like that. There's all sorts of data types that you find in every programming language, strings and booleans and numbers. One of the things we know about programming is indentation. Should we forget about indentation with functional I don't think so. We have namespaces because you need to segregate those names so that they don't collide. We know that. There's arrays and hashes or maps. If you're doing object-oriented programming, then you have classes and inheritance and methods. And then finally, we have programs, right? And this is, sort of everything we know about programming if we're doing object-oriented programming. Are we going to forget all of this? Are we going to forget about indentation? Really? Comments? No, of course not. What we really want to do with functional programming, I think of it as more of a refactoring, okay? And it's more like I'm going to take some of the things that I know about programming and hold on to them, but I'm going to refactor my ideas of how to do programming. So I think of it, imagine you're working on some ordinary application. I don't know, an accounting application, and I apologize to the people who actually work on accounting applications. I think of those as sort of the dull applications, but some application. And maybe your application, it has a design. There's a series of modules or services, and they all go together reasonably well. And it's not perfect, but it works, and it's okay. You have a pretty good design. But time goes by, and requirements change, and you start fixing bugs, and maybe you add a new module, rearrange things a little bit, maybe you add another one, maybe you get rid of a couple because you don't need them anymore, and then maybe you start adding dependencies that weren't there before, right? This is what happens in ordinary systems as they go through their life. And after a while, you start to develop what we technically call a mess. Right? It gets to the point where it works, but it's hard to explain. It works, but the next bug that you have to fix is really a lot harder to fix than it should be. And you spend a lot of time. You know you're in this situation when somebody says, how does this thing work? And you say, well, it works this way, except when this happens, except when you have this. Except on Tuesdays when it's raining. You know, we've all been there, right? The thing is just, it works, and maybe the users or the customers, they like it, but it's just getting hard and messy. And so what do you do in those situations? I've got my accounting system, and it's just kind of become a mess. Well, if you're lucky, your boss, or maybe you, whoever is making up their mind, you sit down and you say, I'm starting with a clean sheet of paper. I'm starting with a completely clean sheet of paper. Now, here's the funny thing about clean sheet of paper. We're going to redesign the system. There's a clean sheet of paper. What's the first thing you do when you redesign something from a clean sheet of paper? Funny thing is, you pull in all the pieces that already work, right? Nobody rewrites something from the ground up, every single line. Frequently, when you're rewriting a system, refactoring, redesigning it, what you do is you pull in all the pieces. You say, oh, this piece works fine. It's just sort of out of sync with everything. This other piece works fine. Maybe I'm going to change them a little bit, but there's pieces that work okay. There's pieces you throw away, certainly, but there's pieces that you keep. So then you have all these pieces that work, and what you say is, the reason my design is not working is because the pieces, I don't have an overriding idea of how they all go together. I need a paradigm to pull this system together. So a redesign is mostly, or a refactor is mostly, let me reorganize the pieces that I have, maybe add some new ones with a new paradigm. So maybe in our accounting system, we have a message bus. So we pull all of our pieces together, but we have this new organizing idea. It's a message bus. All right. Well, what about programming? Is programming, and by programming I mean sort of the traditional kind of mainstream object-oriented programming, is that getting messy? Does that need refactoring? I think maybe it does. And so you remember I said, oh, it works this way except on Tuesdays, Thursdays, and Saturdays, right? That's one of the signs. Well, this is from the Java tutorial. During type erasure's process, first bound if the type parameter is bound, or object if the type parameter is unbounded, right? It has that feeling of sort of ad hocness that, you know, it's the Tuesdays, Thursdays, and Saturdays thing. And I don't mean to pick on Java, right? I think this is kind of a sign that maybe the object-oriented thing has gotten to the point where it's not really working for us anymore. One thing I am sure of is that if they ever build a monument to programmers, to software development, maybe a giant statue of a keyboard or something, there'll be a plaque at the bottom. One thing I am absolutely sure of is those words will not be on the plaque, right? No. But it's not just Java. I quite like Ruby. And here's a description of how protected methods work in Ruby. But the receiver is always self. It's defining class or an object that it's sort of complicated. But for the ultimate in this sort of thing, you just look to C++, which is just kind of full of convoluted rules like this. Okay, so maybe our object-oriented approach to life, to programming, has gotten a little messy. Maybe we need to do something else. Maybe we need to start with a clean sheet of paper. And if I have any sympathy for the forget everything you know about programming, it's starting with this clean sheet of paper. Except the first thing we do with a clean sheet of paper is we pull in all the stuff that works, right? The idea of a program or a service works. We can keep that. Namespaces work, arrays work. Now, maybe we're going to change these things a little bit as we go, but all of the stuff works. We are not going to throw away the idea of a string, right, in functional programming. You don't have to forget everything. All right, so like our accounting system, what we're looking for is a new organizing principle. We need a new paradigm for pulling all the stuff that works into a whole, into a functional whole. So where can we find a new paradigm? Well, it turns out there's another group of people, there's another bunch of people who are doing work very similar to the work that we're doing, the mathematicians. Now, it wouldn't be any surprise if I told you, right, that there's a huge overlap between computer science and math. I think computer science probably is a sub-branch of mathematics. But I think what we as working software developers don't really appreciate is that mathematicians, you know, the people who do the really serious stuff, they have the same kind of problems that we have in terms of, so if you ever like designed a system, and you say, oh, I'm going to have this abstraction, and that's going to be a part of my system, and I'm going to have this other one, and I'm working to a point where I want to have my system do something. And then you've got 5 or 7 abstractions, and you're trying to keep them all in your head, and you're making notes and writing all over the whiteboard, trying to hold all of those abstractions together till you get to the point where you've done something where it's functional. Well, mathematicians do very much the same thing, at least the abstract ones. This is the cover of a book called Principia Mathematica. It was published in the early 1900s by 2 British guys. And what they were trying to do is derive all of mathematics from very simple principles, right? And let me tell you, this is serious stuff. Let me also say, I have never read this book, so I don't pretend, but it is just page after page after page of the most ridiculous abstractions you can imagine until you get to this page. And on this page, in the middle of this page, they prove something really interesting. 1 + 1 = 2. Now, you think your life is hard? Pity the mathematicians, because there's 2 significant things on this page. 1 + 1 = 2, and the page number. Look at the page number. It's 379. It took them 379 pages to prove that 1 + 1 = 2. Mathematicians have the same kind of problems. They've got these abstractions that they are trying to drive towards some goal, something. In this case, 1 + 1 = 2. All right. Is there something we can borrow from the mathematicians that will help us? Do they have some organizing principle that helps them do their work that maybe we can steal? And the answer is yes, they have functions. And you say, well, we have functions, subroutines, procedures, methods. It's not the same thing. A mathematical function is a relationship between 2 sets. Okay? There's like the input set and the output set. And it's a mapping from one to the other. Okay? There's no time involved. It's not like you mathematicians in principle compute a function, really. It just is, right? This is very abstract stuff. So this might be the function for like double the number. 1 goes to 2, 4 goes to 8, that kind of thing. Now, these things are different. The mathematical idea of a function is different than our idea of a method, a procedure, a subroutine, or a function, those things that we have, because our things are code. They're a mechanism. And in principle, our subroutines, procedures, functions can delete a file, they can update a database, they can compute some result from the input, they can change the input, they can compute nothing, return nothing, right? We can do anything we want. It's just some code. And it's not quite the same thing as a mathematical function. Mathematical function, it's always the same. For any given input, it always gives you the same output. It's not like 5 can give you 42 on Tuesdays, Thursdays, and Saturdays, and other time. No, that would be a different function. And in particular, they don't change over time, mathematical functions. It's summer, rain, spring, it doesn't matter. They're always all the same. Mathematical functions are also a thing, right? They're values that you can manipulate. And if this were 10 or 15 years ago, I might go into a long talk about first-class functions. I think first-class functions have kind of seeped into all of the major languages, right? A function is a thing you can make, or really a procedure, a subroutine. Our computery things are also things that you can make. They're values that you can pass around. First-class functions in a programming language. All right, so what if we wanted to borrow this idea of a function from the mathematicians? Well, really, we can't really borrow it, because theirs is completely abstract. But we can have a bunch of rules on our functions that make our functions act something like the mathematical functions. People call functions that behave according to these rules pure functions. It's not a term I really like because it's sort of like good, bad, And this is an engineering decision. So what if we just made these completely arbitrary rules and applied them to our programming things? And the main rule is that you only look at your input, you only look at the parameters, and you only produce output. You only produce the result. Okay? So what does that mean? That means no changing anything, no side effects, no going in and changing the fourth element of your array if there's an array parameter. It means no deleting the file, updating the database, none of that. You just look at the parameters and transform them into some output. All right. We're doing this in the hope that it will make our programs easier to write, easier to understand. And that is the only reason we're doing it. It's not a good, bad thing. It's just we're doing it in the hope that it will make our programs easier to understand. Well, would it actually make our programs easier to understand? Well, maybe. And here's why. Let's say we start with the 3-element array, x. And we call some function on x. And that function is a function that obeys these rules. So we produce some output, y, from that function. Now the question is, what's x at the end of this? It's the same thing. Those are the rules. Okay. So now, what if instead of just calling one function, we call some incredibly complicated combination of functions on x, right? Just an absurdly complicated sequence of functions to compute y. What's x? It's the same thing, all right? You can see how these rules might actually help you make sense of your programs, right? I have this thing, I call a bunch of functions, I still have the same thing. I don't have to look through 25 pages of code trying to figure out if somebody stuck something in the middle of x or something. All right, so here's what we're going to do. We started with our clean sheet of paper, and we pulled in all of the pieces of our current programming language that we thought might work for us, that we thought are working right now. And now we're going to pull in these special rules for functions, okay? And we're going to see where that gets us. All right, so we think about that for a while, and then we have a problem. And the problem is that in most programming languages, data structures like arrays and hashes or maps and lists and things like that, they're mutable. So if you had a little 3-element array, anytime you felt like it, you could look at that middle element and jam some other value in it. You can mutate your array. All right, that's a problem because if we go back to our example and we have that incredibly complicated functional expression there in the middle, and we changed it a little bit, so that we just jam a new value in X. Now we are right back to having to look through all of this code to try and figure out what's X. And that we've just lost any gains that we thought we might get. So I'd like to propose a radical solution to fix this particular problem. Let's make all of our data structures immutable. Once you make that array, you can't change it. Once you make that hash or map, you can't change it. We're just going to make them completely immutable. You can see how that fixes the problem, right? I am now unable to change any of the data in my data structures. But it might feel like, well, how do you get anything done if you can't mutate anything? The answer is really quite simple. We provide all of our data structures with an operation which says, give me a copy of yourself that's just like you, except a little different. So give me a copy of yourself, Mr. ABC array, that's exactly like you, but the middle element is Q. If it's a hash or a map, give me a copy of yourself that has all the keys associated with the same values, except for this one, which is different, or this new one, or delete one, okay? So we do that, and now we no longer have to worry about anybody changing our data out from underneath us. But now we have another problem. And that other problem is copies, right? And you could sort of frame it this way. What if I have a 1,000,000 element array, and I want to change 3 elements in the middle? Do I change the first one and make a copy of 1,000,000 elements, and then change the second one and make another copy? And after a while, I've got 3 or 4 million elements of arrays that I've kind of created and things like that. It turns out, no, you don't have to do that. So there's the problem, right? Am I going to copy? I've got a 27-element array here. I'm trying to mess with the element in the middle. Do I have to copy all 27 elements? It turns out we can do better than that. It turns out some very clever people have come up with something called persistent data structures. And here, persistent doesn't mean saved to the database or saved in a file. It's just an unfortunate word they picked for something completely different. But what persistent data structures are is they're versions of all the familiar data structures, things like arrays and hashes and lists and trees and all of that. There's basically one for all of the familiar data structures. And they have 2 key characteristics. One, they're immutable. And 2, they support this copy on modification operation, but they do it very efficiently without a lot of copying, which seems ironic. The way it works is, think of that 27-element array, right? And what if you implemented that 27-element array, all the letters of the English alphabet, I guess, and the exclamation point, what if you implemented it as a sort of tree? And each tree node has sort of 3 slots. So each node is like a block of 3. And that block of 3, if it's an interior node, either points at something, or if it's a leaf node, it actually has the data, okay? And this is how I represent my array sort of behind the scenes. Well, if I want to get at the 22nd element, I just have to traverse a couple of nodes, and I'm there at my 22nd element, right? But what happens if I want to modify this thing, which really means make a modified copy of this thing? Let's think of how much copying we actually have to do. Well, if we want to modify the middle element there, well, obviously we'd have to copy that little 3-node block there. We'd have to copy the one that points at it. We'd have to copy the one that points at it. And then we don't have to copy anything else because we can reuse everything else from the original. So you get this, the new one and the old one share most of the data, particularly as the data gets bigger and bigger and bigger, which is exactly what you want. Now you might be thinking, but what if that data in the old one changes out from underneath me? It's all immutable. So you see how this all sort of hangs together? All right. So that, I think, solves our problem of immutability in principle. Now, I'm showing this as 3 elements. But and that's just to get it on the slide. In real life, people tend to use more like a branching factor of 32, so all of the nodes are 32 wide. And if you do the math, it turns out that a 3-element tree like this with 32 wide nodes, you can support more than 1 million elements. So it's really pretty efficient if you put your mind to it. All right, so here's my hokey icon. It's a lock for immutable data structures. So we've now got everything that we borrowed from our original language. We've got these mathematical, like pure functions, and we've got immutable data structures. All right, and we've now built this lovely functional world. We've built this lovely functional world where there are no side effects, and the programs are easy to think about because you never have to like dig in to see who the heck is changing my array. And now we have another problem. And that other problem has to do with those side effects we got rid of. You see, if people still used business cards, I would print business cards and I'd have my name on it. And the only thing the business card would say is side effects. If you think about what a side effect is, like writing a file or deleting a file, or updating a database, or hitting some service, side effects are what we get paid to do. All of the things that our customers care about are side effects. Our customer does not care about our code, right? We care about the code. We want the code to be easy to understand. Fundamentally, the person behind that accounting system, the banker or whoever, does not care at all about the accounting system. They care that the database is updated, that the reports are generated, that the files are created, that the services are hit. Right? We are all in the side effects business, right? And in fact, our customers don't think of them as side effects. They think of them as the desired effect. And what we've just done is we've built this beautiful, lovely, functional environment that can't do anything, right? Which seems to be a little bit of a problem. So what we need is a bridge from our beautiful, lovely, functional code into the real messy world of side effects, right? We want our programs to be able to do stuff. So how do we do that? Well, here is the point where I have to sort of take off my functional hat and put on my Clojure hat, because all functional programming languages sort of approach this problem differently. But in general, they're kind of the same. But here's some of the Clojure solutions to the bridge to the outside messy world. One problem in the outside messy world is, how do I implement mutable state within my program? Okay, think of like the classic hit counter in a web application. Congratulations, you're the 57th visitor to this web application. If you think through the functional world that I just described, you can't do that. There's no mutable state. There's nothing that can change. So what we need is some way to represent mutable state. What Clojure does this through something called atoms. And an atom is the closest thing that Clojure has to a variable. It's a container for some mutable state. That's what an atom is. Well, that sounds like a variable. What's the difference? The difference is the way you update an atom. Because an atom is a bridge between the lovely functional world that we've built and the messy outside world that people pay us to mutate and affect. And the way you update an atom is you throw a function at it. Okay, so if it's a hit counter, you would throw a function at the atom that knows how to increment a number. And what the atom does is you throw a function at it, the atom takes that function, gets the current value of the atom, sends that into the function, gets the result that comes out of the function, so it evaluates the function, and the value that comes out of the function becomes the new value of the atom, right? It's a bridge between the nice, clean, functional world on the one side and the messy, stateful world of the real life on the other side. Now, to get a real feeling for like the power of this kind of approach, let's think about what happens if you have you're trying to update this atom on 2 different threads, and the updates come in at the same time, right? This is the classic, oh, geez, I don't want to lose an update kind of problem that anyone who's ever messed with threads is familiar with. Well, what atoms do is, both of the functions will come in. They'll both see the same value of the atom, 59. And, this is where the trouble is lurking because we don't want to lose an update. They will both calculate 60 as the new value of the atom, but one of those functions will get in a little faster and change the value to 60. And what will happen at that point is the atom will notice that when the second function comes in and tries to update the atom, it will notice that the value changed out from underneath it. And what does it do? It just runs the function again. This is sort of collision detection and rerunning. So it's similar to what a database does with transactions. Now you might be thinking, oh, is it okay to run that function a second time? What about side effects? Guess what? There are no side effects allowed. The only side effect is updating the atom, and that's what we're controlling. So atoms are a lovely bridge between the clean functional world that we're building and the messy outside world, and are the things that Clojure uses to maintain program state. Okay, there's another stateful problem, which is, how do I update the database, delete the file, write the file, hit the web service, the sort of, I need to do something to the outside world. And there's a bunch of different solutions to this, including a bunch inside of Clojure, but most of them all rely on some kind of queue. And you put requests of one kind or another on the queue, and then there is some nasty, stateful, side-effecty code connected to the queue, which is pulling things off the queue and doing things with it. So you put a request, hey, update the database, and somewhere on the other side of the queue is some messy code that is pulling that request off and doing something side-effecty, right? The reason you have the queue there is then you can sequence. There's a clear sequence of these operations so that things don't sort of happen all at the same time. Clojure agents, which is one form of this thing, have the same kind of bridge to the functional world that atoms do, in that what you throw at the agent is not data, but you throw a function at it, and the function gets executed in sequence, and it's the thing that does the nasty, stateful, write the file, delete the file, whatever. All right, so here is our functional world, right? We have all the things we pulled in from our old programming style, arrays and namespaces and things like that. We have these pure mathematical style functions. We have immutable data structures. And we have the bridge to the outside, nasty, stateful world. All right, and that's, as far as I'm concerned, that is what functional programming is. That is functional programming in a nutshell. You don't have to forget everything you know about programming. So what's it like to program in a functional style? And in particular, what's it like to program in a functional style if you're new at it? Yeah, no. There is no magic here, okay? I think it's a better way to write programs, but there is no magic, none, okay? You still have off by one errors. This is a new slide. I put this slide in day before yesterday because the day before that, guess what? I spent half a day finding an off by one problem. You still have those kinds of things. You can still have redundant code. We can be working on something together. And you go down the hall and sit down and write some stuff, and I sit down and write some stuff, and then at the end of the day we realize, oh, we just solved the same problem. Functional programming is not going to help you with that. Maybe it'll help you talk about it and figure it out quicker, but those kinds of things are still going to happen. You can still write bad code, right? I have as many conversations. You know that conversation you have, right? Oh, you're going along, you're in the system, and you find something, and you're like, is this as bad as I think it is? And you go to your colleague, and they're like, yep, that is as bad as you think it is. You still have that. The database is still down, right? Isn't the database always down? One bit of magic that you do have is with threads. One bit of magic that functional programming gives you is with threads. Functions take their input, operate on it, and give you output, right? It reduces the amount of state, but particularly, overwhelmingly, the immutable data structures mean that one thread cannot change the data out from underneath another thread. One thread can get the wrong version of the array or the hash or the whatever it is, but it can't change things out from underneath another thread. And in particular, you cannot get the situation where one thread is in mid-update and the data structure is complete garbage and another thread looks at it. That cannot happen with immutable data structures because the thing is either there or it's not. And the new version either exists or it doesn't. When the new version of your array or your hash or whatever exists, it is at least consistent. So there is some thread magic. It doesn't solve all your thread problems. Think about atoms. But it eliminates a whole class of them. And after all, isn't that what our programming paradigms are supposed to do? So what's it like to program using, effectively, these are rules, right? These are arbitrary rules that we're saying we're going to adopt in our programs because we think that those rules are going to help us build better programs. Well, initially, it feels like programming wearing handcuffs, right? You know, if you've never programmed with immutable data structures, you spend your first week like, oh, I'll just change the third element in that. No, I can't. I need to return something. And it really feels like you are burdened by all of these rules, and it's hard to see why you have to program with these rules in your gut. But you do it for a while, and after a while you realize that, oh, okay, my code is easier to understand. I can reason about the code because I spend a lot less time looking through all the code to see what's going on. And after a while, those handcuffs feel like a bicycle, right? A bicycle, right? You got to hold your arms like this. There's all kinds of rules in riding a bicycle, right? Most of us can only ride a bicycle on a pretty flat, even surface, but it reduces the friction between you and where you want to go. And that really is my feeling about functional programming. All right, so how much time do we have left? All right, we're doing pretty well. So does it work, I think, is the final question I want to try and answer. And for that, I'd like to introduce you to Pedestal. Pedestal is a library, or actually a set of libraries. It's produced by the company I work for, Cognitect. And Pedestal, and it's open source, and it's widely used in the Clojure world. So forget about the fact that it's produced by my company. That's not really important. It happens to be a production library that I'm familiar with. And Pedestal is that library in the Clojure world that, oh, I've got a request that came in. I need to parse the parameters. I need to route it to the right place. I need to authenticate it. Pedestal provides the plumbing to do all of that. It's that library, right? There's basically one or more in every programming environment. Okay, but think of it, Pedestal is just a giant pile of production Clojure code written in a functional style. So let's look inside Pedestal. What is in Pedestal? Well, there's 18,706 lines of code in Pedestal as of last week. I got to tell you, Clojure is a pretty dense language. So almost 19,000 lines of code, that is a lot of Clojure. That is more Clojure than is in most applications. Okay, if we look a little deeper, what's in those about 19,000 lines of code? There's 28 protocols. A Clojure protocol is a bundle of method signature or function signatures, and it's the way that you define interfaces between different parts of a Clojure application or library. Makes sense that a library would define a bunch of interfaces, so there's 28 protocols in Pedestal. There's 8 of these bridges to the outside world, right? Agents and atoms and things like that. There's 9 record types. A record type in Clojure is as close as Clojure gets to object-oriented programming. It's like, here's a thing, and it has these fields and these operations. There's 9 of them. There's one multi-method. a multi-method is a completely general form of polymorphism, all right? And then there's 944 functions. Think about that. There's all of those small numbers, there's 28 of these, and 8 of these, and 1 of these, and then there's 944 functions. And if you don't remember anything else from this talk, remember this pie chart. This giant pile of production functional programming is almost entirely functions. And it has a little sliver of interfaces and then a trivial amount of everything else. And if you want to know what functional programming is like for I get up every morning and I write applications kind of programmer, it is this. You spend all of your time, or most of your time, just writing functions. If that sounds a little boring, yes, it is boring. It is boring in that good way of I can do the same thing over and over and over without having to negotiate with my language, without having to negotiate with libraries. I just write these testable, straightforward functions for the most part, and then maybe a few protocols. So there we have it. That's kind of the working programmer's guide to functional programming. Does it work? I think so. I hope you'll try it and find out for yourself. Thanks for listening.